Quantum computers use the natural world to produce machines with staggeringly powerful processing potential.
I think it's going to be the most important computing technology of this century, which we are really just about 1/5 into.
We could use quantum computers to simulate molecules to build new drugs and new materials, and to solve problems plaguing physicists for decades. Wall Street could use them to optimize portfolios, simulate economic forecasts, and for complex risk analysis. Quantum computing could also help scientists speed up discoveries in adjacent fields like machine learning and artificial intelligence. Amazon, Google, IBM, and Microsoft, plus a host of smaller companies such as Rigetti and D-Wave, are all betting big on quantum.
If you were a billionaire, how many of your billions would you give over for an extra 10 years of life? There are some simply astonishing financial opportunities in quantum computing. This is why there's so much interest, even though it's so far down the road.
But nothing is ever a sure thing, and dealing with the quirky nature of quantum physics creates some big hurdles for this nascent technology.
From the very beginning, it was understood that building a useful quantum computer was going to be a staggeringly hard engineering problem, if it was even possible at all. Right? And there were even distinguished physicists in the 90s who said this will never work.
Is quantum truly the next big thing in computing? Or is it destined to become something more like nuclear fusion, destined to always be the technology of the future, never the present? In October 2019, Google made a big announcement. Google said it had achieved quantum supremacy. That's the moment when quantum computers can beat out the world's most powerful supercomputers for certain tasks.
They've demonstrated with the quantum computer that it can perform a computation in seconds what would take the world's fastest supercomputer years, thousands of years, to do that same calculation. And in the field, this is known as quantum supremacy, and it's a really important milestone.
Google used a 53-qubit processor named Sycamore to complete the computation, a completely arbitrary mathematical problem with no real-world application. The Google quantum computer spit out an answer in about 200 seconds. It would have taken the world's fastest computer around 10,000 years to come up with a solution, according to Google scientists. With that, Google claimed it had won the race to quantum supremacy. But IBM had an issue with the findings. Yes. IBM, the storied tech company that helped usher in giant mainframes and personal computing, it's a major player in quantum computing. IBM said one of its massive supercomputer networks, this one at the Oak Ridge National Laboratories in Tennessee, could simulate a quantum computer and theoretically solve the same problem in a matter of days, not the 10,000 years that Google had claimed. Either way, it was a huge milestone for quantum computers. And Silicon Valley is taking notice. Venture capital investors are pouring hundreds of millions of dollars into quantum computing startups, even though practical applications are years or even decades away. By 2019, private investors have backed at least 52 quantum technology companies around the world since 2012, according to an analysis by Nature. Many of them were spun out of research teams at universities. In 2017 and 2018, companies received at least $450 million in private funding, more than 4 times the funding from the previous 2 years. That's nowhere near the amount of funding going into a field like artificial intelligence. About $9.3 billion worth of venture capital money poured into AI firms in 2018. But the growth in quantum computing funding is happening quickly for an industry without a real application yet.
It is not easy to figure out how to actually use a quantum computer to do something useful, right? So nature gives you this very, very bizarre hammer in the form of this interference effect among all of these amplitudes, right? And it's up to us as quantum computer scientists to figure out what nails that hammer can hit.
That's leading to some backlash against the hype and concern that quantum computing could soon become a bubble and then dry up just as fast if progress stalls. Quantum computers are also notoriously fickle. They need tightly controlled environments to operate in. Changes in nearby temperatures and electromagnetic waves can cause them to mess up. And then there's the temperature of the quantum chips themselves. They need to be kept at temperatures colder than interstellar space, close to absolute zero. One of the central tenets of quantum physics is called superposition. That means a subatomic particle, like an electron, can exist in two different states at the same time. It was, and still is, super hard for normal computers to simulate quantum mechanics because of superposition.
Now, it was only in the early 80s that a few physicists, such as Richard Feynman, had the amazing suggestion that if nature is giving us that computational lemon, well, why not make it into lemonade?
You've probably heard or read this explanation of how a quantum computer works. Regular or classical computers run on bits. Bits can either be a 1 or a 0. Quantum computers, on the other hand, run on quantum bits, or qubits. Qubits can be either 1 or 0, or both, or a combination of the two at the same time. That's not wrong per se, but it only scratches the surface according to Scott Aronson, who teaches computer science and quantum computing at the University of Texas in Austin. We asked him to explain how quantum computing actually works.
Well, let me start with this. You never hear your weather forecaster say, well, there's a negative 30% chance of rain tomorrow, right? That would just be nonsense, right? The chance of something happening is always between 0% and 100%. Okay, but now quantum mechanics is based on numbers called amplitudes. Amplitudes can be positive or negative. In fact, they can even be complex numbers involving the square root of -1. So a qubit is a bit that has an amplitude for being 0 and another amplitude for being 1.
The goal for quantum computers is to make sure the amplitudes leading to wrong answers cancel each other out, and that scientists reading the output of the quantum computers are left with amplitudes leading to the right answer of whatever problem they're trying to solve. So, what does a quantum computer look like in the real world? The quantum computers developed by companies such as Google, IBM, and Rigetti were all made using a process called superconducting.
Okay, and this is where you have a chip the size of an ordinary computer chip, and you have little coils of wire in the chip, which are actually quite enormous by the standards of qubits. They're nearly big enough to see with the naked eye. Okay, but you can have two different quantum states of current that are flowing through these coils that correspond to a 0 or a 1. And of course, you can also have superpositions of the two. Now, the coils can interact with each other via something called Josephson Junctions. Okay, so they're laid out in roughly a rectangular array, and the nearby ones can talk to each other and thereby, generate these very complicated states, what we call entangled states, which is one of the essentials of quantum computing. And the way that the qubits interact with each other is fully programmable. Okay, so you can send electrical signals to the chip to say which qubits should interact with each other ones at which time. Now, in order for this to work, the whole chip is placed in a dilution refrigerator that's the size of a closet, roughly, and that cools it to about 1/100th of a degree above absolute zero. That's where you get the superconductivity that allows these bits to briefly behave as qubits.
At IBM's research lab in Yorktown Heights, New York, the big tech company houses several quantum computers already hooked up to the cloud. Corporate clients such as Goldman Sachs and JP Morgan are part of IBM's Q network, where they can experiment with the quantum machines and their programming language. So far, it's a way for companies to get used to quantum computing rather than make money from it. Quantum computers need exponentially more qubits before they start doing anything useful. IBM recently unveiled a 53-qubit computer, the same size as Google's Sycamore processor.
We think we're actually going to need tens of thousands, hundreds of thousands of qubits to get to real business problems. So you can see we need quite a lot of advances, and doubling every year, or perhaps even a little faster, is what we need to get us there. That's why it's 10 years out, at least.
Quantum computing would need to see some big advances between then and now, bigger advances than what occurred during the timeline of classical computing and Moore's Law.
Oh, we need better than Moore's Law. Moore's Law was doubling every 2 years. We're talking doubling every year, with occasionally some really big jumps.
So once quantum computers become useful, what can they do? Scientists first came up with the idea for quantum computers as a way to better simulate quantum mechanics. That's still the main purpose for them, and it also holds the most money-making potential.
So one example is the caffeine molecule. Now, if you're like me, you've probably ingested billions or trillions of caffeine molecules so far today. Now, if computers are really that good, right, really that powerful, and we have these tremendous supercomputers that are out there, we should be able to really take a molecule and represent it exactly in a computer. And this would be great for many fields: healthcare, pharmaceuticals, creating new materials, creating new flavorings, right? Anywhere where molecules are in play. So if we just start with this basic idea of caffeine, it turns out it's absolutely impossible to represent one simple little caffeine molecule in a classical computer, because the amount of information you would need to represent it, the number of zeros and ones you would need, is around 10 to the 48th. The number of atoms on the Earth are about 10 to 100 times that number. So in the worst case, one caffeine molecule could use 10% of all the atoms in the Earth, just for storage. That's never going to happen. However, if we have a quantum computer with 160 qubits, and this is a model of a 50-qubit machine behind me, you can kind of figure, well, if we make good progress, eventually we'll get up to 160 good qubits. It looks like we'll be able to do something with caffeine on a quantum computer, and it's never going to be possible on a classical computer.
Another potential use comes from Wall Street: complex risk analysis and economic forecasting. Quantum computing also has big potential for portfolio optimization. Perhaps the biggest business opportunity out of quantum computing in the short term is simply preparing for the widespread use of them. Companies and governments are already attempting to quantum-proof their most sensitive data and secrets. In 1994, a scientist at Bell Labs named Peter Shor came up with an algorithm that proved quantum computers could factor huge numbers much more quickly than their classical counterparts. That also means quantum computers, if powerful and efficient enough, could theoretically break RSA encryption. RSA is the type of encryption that underpins the entire internet. Quantum computers, the way they're built now, would need millions of qubits to crack RSA cryptography. But that milestone could be 20 or 30 years away, and governments and companies are beginning to get ready for it.
For a lot of people that doesn't matter. But for example, for health records, if health records could be opened up, that could compromise all kinds of things: government communications, banking records. Sometimes even banking records from decades ago contain important information that you don't want exposed. So the problem we've got is we don't really know when quantum computers will be able to do this, or even if we'll ever build one big enough to do this. But what we do know is if you don't update your cryptography now, all the messages that you send over the next few years, the ones in history, could potentially be read. What this means is, for example, if you're a Cisco selling networking equipment, you're going to need to offer quantum-safe encryption as an option in the very near future, because even though it doesn't look like we need it right away, if your product doesn't have it and a competitor does, guess which product gets bought?
One big issue facing quantum computing, other than increasing the number of qubits while keeping things stable, is that no one actually knows the best way to build a quantum computer yet. The quantum computers that Google and IBM and other companies show off are very much still experiments. There's also a big education gap. Not many people are studying quantum computing yet. China is pouring billions into quantum computing education, and the US Congress passed a law in 2018 called the National Quantum Initiative Act in order to help catch up.
Quantum computing capable people will be a rare commodity, which means that you want to invest in them now. You want to be hiring people with quantum computing knowledge, not necessarily to do quantum computing, but because you want that intelligence in your organization so that you can take advantage of it when it shows up. Now, China, with its promise to put $10 billion in, is really upping the stakes in terms of the number of Chinese quantum physics PhDs that are going to start appearing. And if that hair restoration or life extension drug happened to be property of the Chinese government, what does that do to the world economy? That's much more powerful than making war.
Other experts have compared Google's announcement to Sputnik, the Soviet satellite launched into orbit in 1957. The beach ball-sized satellite was the first man-made object to orbit the Earth. But Sputnik didn't really do anything useful, other than prove launching something into space was possible.
Many people are surprised that where exactly we are. For those who are just getting started, they like to make noise about vacuum tubes and Sputnik and things like this. But let me give you some numbers. IBM has had quantum computers on the cloud for 3.5 years, since May of 2016. We're not in any sort of Sputnik era. We're not landing on the moon. But for those of you who like space history, I think we're probably well into Mercury or Gemini.